We are going to train our neural network, that is, adjust the weights and biases of the network using an optimization method known as gradient descent. I should mention that gradient descent is very widely used in many different problems, and therefore let's take a look at how gradient descent works. So in our context, we have a cost function, the cost of the network, which we've discussed earlier, which is C. And we want to find the parameters that minimize the cost. And let's focus on a network with essentially two parameters. One weight, which we'll say is Wi, and one bias, which is Bj. So it's a two-dimensional function in this case. If we happen to know the entire cost function, it would be easy to apply an algorithm to find the minimum, and then we can simply read out the Wi and Bj corresponding to that minimum. But all we have is the cost corresponding to a particular instantiation or for specific values of Wi and Bj. So let's say this is where what your initial cost is. That is, these are the values of Wi and Bj to start off with. We essentially want to update the weight and the bias so that with each update we reduce the cost and finally end up at the minimum of the cost function right here and find the corresponding values of Wi and Bj. That's our goal. So we are interested in making these updates and also measuring the change in the cost because of these updates. So how do you measure the change in a function? For this, we appeal to something we've discussed at great length before, which is the Taylor series. So let's say you have a function which is f of xy, two-dimensional function. If you want to find the value of f at x plus delta x, y plus delta y, Taylor series tells us that that's approximately equal to, at least as a linear approximation, f of xy plus the derivative of f with respect to x times delta x plus the derivative of f with respect to y times delta y. So in other words, the change in f due to the change in x and y is approximately equal to the first derivative of f with respect to x times delta x plus the first derivative of f with respect to y times delta y. So this is known to us. So we can now do the same for our cost function. So simply replace f with the cost function and x and y with our parameters Wi and Bj. So you have the derivative of c with respect to Wi times the change in Wi plus the derivative of c with respect to Bj times the change in Bj. This can be written in vector form as follows. So you have your derivatives, the first derivatives, the partial derivatives or pure derivatives in this vector right here, and the changes in the parameters in this vector right here. This should appear familiar to you. If you remember when you talked about edge detection, we talked about the gradient operator, which was the first derivatives of the image in the x and y direction. So similarly, we have the derivative of the cost function with respect to Wi and Bj. So we can call this the gradient. This is a gradient operator applied to C. So this is the gradient of C, this vector right here. And you have the change in the variables. We'll call the variable vector v, so the change in variables is delta v. And del C times delta v is equal to the change in the cost right here. So we can take a closer look at that expression. So you have delta C is equal to del C times delta V. And now we can play a little trick here, which is that the gradient applied to the cost function gives you the two gradients, which are telling you in which direction you're climbing, increasing the cost the most. That's this direction right here. And basically what we want to do is make changes to the variables in the direction that is opposite to this direction. That's essentially what gradient descent does. You're descending. You're actually moving in the opposite direction steepest descent. So if you simply set delta V is equal to minus of the gradient of C, that's this direction right here, then you're going to be heading in the right direction. If you substitute that back into this equation, you get the change in cost is equal to minus the gradient of C squared, magnitude of that squared. And we can make one little change here, a little bit of a twist, which is we can introduce a parameter eta, which we will call the learning rate. And so that tells you how fast you're going to move, how fast you're going to descend. That we call that the learning rate. And so we say that delta V right here is minus eta times the gradient of C. And so you now have the change in cost is equal to minus eta times the gradient, the magnitude of the gradient of the cost squared. So that's it. We know how to change our parameters. That's right here. So you have your existing parameters, you find the gradient of the cost, the two derivatives in our case because we have two parameters, multiply them with eta, subtract that from the current parameter values wi and bj, and you have your new parameter values wi prime, bj prime. This is your update rule. It's very, very simple. The only requirement is that for each iteration, you need to find the derivative of the cost function with respect to all the parameters. Okay, now let's take a look at the effect of this parameter eta or the learning rate. Well, that's very easy to see. If you use a very small learning rate, then you're going to move towards the minimum slowly as shown here. You see that? Moves very slowly. If you use sort of an optimal or a moderate eta value, then you're going to move pretty fast and converge faster. Less computations is what that means. However, we can't go too far with this. If you use a very large value, you can actually overshoot. So if you use a large learning rate eta, you can actually end up bouncing around quite a bit before you arrive at the minimum. But there's an additional problem. You might not actually arrive at the minimum. The reason is that you might overshoot to such an extent that you might end up in another valley in the cost function and end up converging at the wrong local minimum. So that's the effect of the learning rate. So just to give you a little bit more intuition for how gradient descent works, I'm going to use this sort of caricature right here. Imagine that this is some mountainous, hilly terrain, and you happen to be standing right here. And your singular goal is to get to the lowest point in this terrain. All you need to know is a way to find the derivative, the gradient of the terrain at this particular point. So you find the gradient of the terrain, that's going to point in the direction of steepest climb, but you're going to then move in the opposite direction. And if you simply repeat that, you're going to end up at the lowest point in the terrain as such. So that's just to give you sort of a geometric intuition for what gradient descent does. All right, now, in our case, we took the example of two parameters, wi and bj, but obviously we have possibly millions of parameters. So how does gradient descent work for the entire network? Well, it turns out gradient descent really doesn't care what the dimensionality of the problem is. You can apply it to the problem and you keep moving in high dimensional space so that you end up at the final result. The only thing that we have to bear in mind here is that obviously the computations tend to go up with the dimensionality. So how do we do this? For a general multi-layered neural network, you're going to define your change in parameters as the change in all the parameters, all the weights and biases in your network. And the gradient of the cost now is not just a two-dimensional vector, but its dimensionality equals the number of parameters in your network. So in this notation right here, you see here, you have WJKL. J is the neuron, so K is the input, so it's the kth input for the jth neuron in layer L. That's what this notation really means right here. So once you've computed the gradient, and we'll see how we compute the gradient, if you compute the gradient of C, you simply multiply that with eta, some chosen eta, and you end up getting your change or adjustment in your parameters, and then you use exactly the same update rule. You're going to essentially go in here and update the existing parameters to get your new parameters right here. Okay, so now the one thing that we haven't discussed is how do we compute the gradient? Well, we know how to compute gradients using finite differences. We have done this before. So let's say that you want to find the gradient of C, the cost, with respect to one of these weights right here, WJKL. So what you can do is construct a parameter change vector right here, which is 0 everywhere except for WJKL, that particular parameter. And so you can compute the cost for W plus delta W, B, minus the cost for the current network, which is CWB, divided by the amount that you've actually changed the parameter value, which is right here. This is just a definition of finite difference. And the same applies to the biases as well. So this is for weights, this is for biases. Okay, so that's very simple. So conceptually, and even in terms of algorithmically, it's extremely simple to apply gradient computation and gradient descent in general. Now, one thing to note here is that all the gradients end up sharing the initial cost right here. So you do the cost of the network as it stands right now, and that's CWB, and that's reused in all of these finite differences. But unfortunately for us, for each weight and bias, you've got to repeat this process. So the number of gradient computations that you do using finite differences here is equal to the number of parameters that you have. And that can be enormous. And so that's what makes the problem of training really hard if you use your conventional, traditional approach to gradient descent. So let's do some back of the envelope calculations here in terms of the complexity of training. So we're going to use our network here, which was Nielsen's network. This is the one that we were discussing before for the recognition of handwritten digits. And in this case, each gradient computation, we need roughly 24,000 cost computations. That's how many parameters there are, because you have 23,820 weights and 40 biases. So that's where we come up with this number. That's the number of cost computations that we need for one gradient, one iteration of the gradient computation. So with that in mind, we can sort of do a rough calculation in terms of what the complexity of applying gradient descent is. Actually, one iteration of gradient descent to train this network. So the number of multiplications required to compute the cost for a single image is roughly this, 24,000. That's the feed-forward computation that we talked about earlier. And then the number of training images in our case, MNIST, is 60,000. So the number of multiplications required to compute the average cost, because you've got to run all the training images through, is 1.4 times 10 to the power of 9, getting up there. And then the average cost of computations to compute the gradient, this is where gradient descent comes in, with respect to all weights and biases, is again roughly 23,000, 24,000 right there. and then you've got to multiply that with this previous number, and therefore the total number of multiplications required for one iteration, you may need hundreds of iterations, but one iteration of gradient descent is 3.4 times 10 to the power of 13. Very big number. And the question really is, can we do better? Indeed we can, and that's what we'll talk about next.